Hello, everyone. Thanks for joining this lightning talk. My name is Irfan Elahi, and I'm a specialist solutions architect in Databricks. I hope I'm audible. Quick sound check, thumbs up, all good? Great. Today's session is all about race to real time. Fancy name, but basically we'll be talking about building low latency streaming ETL solutions, including the latest and greatest from Databricks using OLTP-DB, aka Lakebase. So if you've been keeping tabs on DICE announcements, you probably know that Lakebase is our managed Postgres offering, tailored for operational as well as GenAI use cases. But that's not all. We'll also unpack key performance optimization techniques to supercharge your solution end to end, ultimately resulting in lower TCO and reduced time to value. Forward-looking statement, it is for information purposes only. And be sure to complete the surveys at the end as well. So this is how we are going to spend the next 20 minutes. We'll first set the scene and the context. We'll try to understand why all of this matters, what's this talk all about, what's the problem that we are trying to solve. And then we'll do a deep dive into the solution design, and we'll also unpack the key performance optimization techniques to achieve sub-2-second latency. And then we'll see everything in action in a live demo and hope everything will go well. OK, so this all started through a POC at a customer end who was in a racehorsing industry. Now, imagine someone, like you are someone who is responsible for running these exhilarating horse races, which, by the way, is pretty popular in Australia, and we even have a public holiday dedicated to horse races, which is personally is pretty cool. Now, what happens in these races is that massive amounts of data floods in real time. For example, horse positions, they change in split seconds. There are jockeys and the track conditions, they change pretty dynamically. And then we have like odds, like who is going to win and whatnot. They fluctuate pretty rapidly as well. On the consumer side, we have fans, leaderboards, and betting applications. All of them need instantaneous updates. So the challenge basically is delivering real-time insights efficiently, cost-effectively, and leveraging the best of Databricks. Now, historically, Databricks pioneered the lakehouse paradigm, unifying data lakes, data warehouses, breaking down the silos, democratizing the data and AI. It is great. But there was one untapped territory or gap. That is an optimal data store for OLTP use cases. And this year at DICE, we have addressed that gap via Lakebase. So we are going from unified analytics to real-time operational use cases. So all of this makes sense, but how does this all work? Like, how does a solution seamlessly integrate with all the different components of Databricks? So you have structured streaming, Photon, Unity Catalog, Delta, and now Lakebase is in the mixture as well. How do you design a solution? So that's one of the key considerations that we'll unpack. And sure, once the solution design is there, how to make sure that what you design is optimized to hit those very aggressive latency targets. In this case, it was sub 2 seconds. So let's dive into that. Firstly, for this POC, the source of the data was in Kinesis, which is a pub/sub service from AWS. So in Kinesis, they were publishing all the data about the race events in real time. Now, we at Databricks natively connect to Kinesis to process the events or data in streaming form. So structured streaming fundamentally is micro-batch based, which, by the way, is changing with the upcoming real-time mode. But still, what happens is that in each micro-batch, chunk of raw events are extracted from, in this case, Kinesis, and they are processed end-to-end. OK, which makes sense. But the other problem comes, as we all know, that the raw data, that is rarely consumable, and we almost always need to transform it, change it, or massage it to make it consumable downstream. So in this case, this POC required joining it with the existing big delta tables to perform lookups for enrichment and augmentation, and also it involved column-level transformations as well. Now, when all the extraction and transformations are done, the data is written out to Lakebase, and in this case, it is written out in 2 steps. Firstly, data is written out to staging table, and then we perform an SCD type 1 merge from the staging table to the target table, orchestrated from Databricks. We'll see how it all works. And once the data is in Lakebase, any downstream consumer can consume it. So in this case, you can have a solution design where the Databricks apps, which were launched at DICE today, these Databricks apps can integrate with Lakebase to perform those single-digit millisecond, super low latency queries to serve your operational use cases. So that's how it looks like from solution design point of view, how all things stack together and integrate together. But OK, that is a solution design. But what about the optimization? What are the key considerations that we need to make sure that, yeah, the solution is optimized, it's not costing you a lot, you're able to hit those latency targets, and ultimately your TCO is optimized? All right. It all starts at the source level. First, we need to ensure that the amount of data that we retrieve from Kinesis, which is basically the size of the micro batch, it is deterministic, and it is controlled or constrained. Now, this is where I see majority of the customers running into some challenges because they don't use the related configs to control the size of your micro batch. So for example, for Kinesis, it's max records per fetch. For Kafka, it's max offsets per trigger. And for Delta or autoloader in general is max bytes per trigger. Now, if you don't use these defaults, if you don't use these configs, then the defaults are either too large or too undefined, then your micro batches become super big. And this have a cascading negative impact on the overall performance of your solution. And then there are configs as well to make sure that you fetch the data as quickly as possible and you process the fetch data as quickly as possible as well. Next, controlling the size of micro batch has a direct impact on the performance of your joins. Now, if you are joining, if you're using Photon, then your joins will already be blazing fast, so that's great. But you can further ensure that Photon chooses the right type of join in this context, that is the broadcast join, in which the small streaming micro batch is copied to each exector, and the need to shuffle around the big table is eliminated. So that's one performance consideration. Now, all these things are chained together. Now, with the broadcast join in place, another key performance optimization technique kicks in, which is dynamic file pruning. This results in massive pruning of your big tables which are being used in your joins. So if we take a step back, broadcast join, it is eliminating the need to shuffle the big tables during the join. But with the dynamic file pruning, you are only reading the files from your object storage, which contain data relevant for your join. We all know reading from object storage is an expensive process. So we can do as much pruning as possible from object storage, whether it's S3 or ADLS, bring in the minimum possible data in memory to perform the computations. The performance gains, they become enormous. When it comes to data skipping at the object storage level, we use liquid clustering, which is the recommended data layout technique in Databricks, potentially replacing partitioning and Z-ordering. And liquid clustering, when used correctly, this makes this whole data skipping business super, super effective. We run these streaming jobs on a cluster which is disk caching enabled. As a result of that, your big tables, they get gradually cached as the micro batches are being processed, reducing the round trips to the object stores like S3, again, resulting in lower latency. We make sure that the query plan, this part that Databricks uses to process your joins, are optimized, courtesy of updated table stats. And if you are now using predictive optimization, this is optimized. This is automated as well. Now, when it comes to writing out to Lakebase, as I mentioned before, it's done in 2 steps. First, the staging table is overwritten, and this part is parallelized. So where each partition of your streaming micro frame or micro batch is written out to the Lakebase. So you achieve some level of good throughput there. And then we perform a native merge natively in Postgres via Postgres native constructs like insert on conflict. We'll see a demo of that. This is orchestrated from Databricks, and it is a single-threaded process. So like driver initiates that insert on conflict thing. And then when the data has reached the target table, you can hook your consumers to your lake base to perform the low-level, single-digit millisecond queries. Now, as a result of when you put all of these pieces of the puzzle together, what you achieved and what we proved in that POC was we achieved sub-2-second latency, ETL latency, end-to-end, and we were able to hit the SLA and expectations there. All right. Let's see everything in action. All right, so we are now in Databricks workspace, and as you can see here that we are using structured streaming. We are connecting to Kinesis, and these are some of the configs that I was specifying, controlling the size of the data that we extract from Kinesis and making sure that we read the data as quickly as possible from Kinesis and process the fetched data as quickly as possible. And then we use the for each path function to define our transformation logic. And this is where the crux of the logic lives. We specify our connection details to lake base and all that. And this is where the key thing is. So we're doing a join between source, which in this case is representing the micro batch, which is coming from Kinesis, with our demo registry table. If you see it in the UC, then it's around 211 GB. We'll see a snapshot of that in the Spark UI. So we're joining these two tables. We're doing some lookups. We're getting some additional information like jockey name, race location, horse weight, doing some column-level transformations. So when that data frame is ready, well, then we write it out to lake base, and that's how it's done. And this is writing to the staging table, and this operation is an overwrite operation. And once the staging table has been overwritten, as I showed in the diagram, we initiate a merge, which is in the world of Postgres, it looks like insert on conflict. So we are reading from the staging table and writing into the target table, all orchestrated within the life cycle of one microbatch. Yep. Okay. Just conscious of the time as well. Yeah, and it's yeah, I think it will be. Yeah. Okay. Thank you for that. So again, quick review of that. So we are doing a join here, and that data is written out to lake base, and this data is written out to staging table. And then we're doing a merge from the staging table to the target table through insert and conflict. Let's run it. And I'm using a cluster which is pretty small. It's just a one-worker cluster, not huge. And we can see here, we can see some stats here. For example, it's running end-to-end, and we are seeing each batch is taking around 1.6 seconds consistently, processing around 14,000 records per second, which was OK for this POC. You can toggle the configs to increase or decrease the throughputs as required. And in here, this is the OLTP. I'm connected to OLTP-DB through pSQL. So we can do a record count of the number of records that are coming through in that table. Right. Hopefully it will. I think its connection is. For the while that refreshes, let me just show a couple of more things in this. So we can go to Spark UI. I wanted to highlight the key. We can close it for now because the performance has been good. Hopefully it will load. That's the joy of live demos. Yep. So let's go to SQL data frame. And we can see all these different, which is representing the joins that are happening. Let's see one of these. So for example, this is the one. Let's see what's happening under the hood in the query plan. So firstly, we can see here that it's using the broadcast join, which is, in this case, the most optimal type of join it's using. And this is a big table, and this is representing that microbatch that's coming in. So these two are being joined. And if you expand this, the key thing to look here is the file that it has pruned. So it has pruned 2,000 files, and it has only read 3 files. In terms of size, if I zoom in a bit, it has pruned 211 GB of data, and it's only read 287 MB of the data. So massive, massive, massive pruning of the big table, only reading a couple of hundred MBs of data to perform that join, and that's the reason that these joins are super fast, getting completed in around 1 second. Switching back to the presentation mode.
So how did you know which job has that? You probably based on.
Yep. It will be good if we take the questions at the end. Will that be okay? Okay. Okay. But that's not the only integration pattern. There are other integration patterns as well. So for example, you can have a data pipeline writing to a Delta table, and then you can have an automatic sync configured from the Delta table to the lake base. So you can cover majority of the use cases. So for example, if the data is in the Delta table, you can use it for the known use cases like ML or warehousing, and data on the lake base can be used for operational and other types of use cases. So that's one. It's pretty hands-off. You just configure it once, and the syncing happens pretty seamlessly at the backend. But it could be other way around as well. So you can have data pipeline writing to lake base, just like we did in this case. But if the same data is needed in your Delta lake as well, then you can configure that auto sync, and the same phenomena will happen, and you can use the data in for the relevant use cases. So that brings me to the end of this demo. Basically, the gist is that you can build pretty powerful low latency streaming ETL solutions using lake base, and this solution design and this pattern basically represents how you can stitch all of these different components together. And while building these solutions, what are the key consideration techniques with respect to performance optimization to make sure that you achieve your latency goals? So I hope the demo and the whole talk has been insightful, and yeah, happy to take any questions now.